Hello everybody, my name is Jacob Mercado. I'm an application engineer working with Lattice Semiconductor, and today I'll be talking to you guys about Reveal and how it can be used to troubleshoot FPGA designs in Lattice Radiant and Lattice Diamond. So without further ado, let's get started. So before we get into the bulk of the training, I first want to quickly introduce myself. So like I mentioned, I'm Jacob Mercado, and I'm a software application engineer working with Lattice Semiconductor. I'm a part of the software tool enablement team, and I specialize in software tool usage, scripting, and simulation. I currently have a master's and bachelor's degree in electrical engineering, which I both got from San Jose State University. So now that I've introduced myself, let's jump into the training. So to begin, I want to give a quick overview of what's planned for today's training. To start off, I'm going to introduce Reveal and all of its main components and features. After that, I'm going to go into a little bit more depth about each of Reveal's main features, beginning with Reveal Analyzer, and then moving on to Reveal Controller. After that, I'm going to summarize what we discussed today, and then go into some frequently asked questions. So without further ado, let's get into it. So for those that are not familiar with Lattice and ARM software tools, Reveal is the primary debugging tool that we can use to debug Lattice FPGA projects targeting Lattice Radiant or Lattice Diamond. The main advantage of Reveal is that it can be used for integrated logic analysis and interactive debugging on device, depending on whichever mode you're using. One other advantage of Reveal is that it can be used to debug designs at various process stages during the design flow, whether it be at the initial implementation level with RTL or later on in implementation after synthesis or PAR. One key thing to remember with Reveal is that it has two main modes, which have different types of debugging supported. The first mode, Analyzer, is used to tap into signals on device and perform logical signal analysis depending on different states in your FPGA's design operation. The second mode, Controller, is used to interface with signals on device and tap into them and control them. One thing to keep in mind with these two modes is that the different software tools support different variations of these, with Diamond only supporting Reveal Analyzer, while Radiant supports both Reveal Controller and Reveal Analyzer. Moving on, let's discuss a little bit more about each of Reveal's two main modes. The first mode, Reveal Analyzer, is primarily used to capture signals on the device, and can also be used to implement logical conditions to determine when you can capture signals. What this essentially means is that you can select specific signals in your design, and then create logical expressions to determine when Reveal should be capturing other signals in your designs in a waveform-like display. Aside from Reveal Analyzer, there's also Reveal Controller, which is another mode which can be used to directly interface with designs to control and monitor signals. Reveal Controller contains several different sub-functions which can be used to do different things like add virtual switches or LEDs to your design, interface with generic memory interfaces, control groups of registers in your design, and also fine-tune hard IP within a design. Now that we've discussed Reveal's two main modes a little bit more, let's talk about some of the use cases in which you might want to use Reveal. The first of which is to identify and diagnose functional issues in the design. Another possible usage of Reveal is to debug your designs at various stages in the implementation process to isolate different stages at which implementation issues might be occurring. Aside from that, like I mentioned, with Reveal Analyzer, you can also tap signals on device and capture waveforms to verify your design's functionality at different conditions. Aside from that, you can also control and interface with your design by driving and monitoring signals using virtual switches and registers. And lastly, another big advantage of Reveal is that you can fine-tune your design's operation by tweaking various register settings for hardened IP blocks on your device. So before we continue on to the next part of the training, one thing I quickly want to overview are a couple of key takeaways that you should know about Reveal. The first key takeaway is that Reveal uses FPGA resources to implement its debug logic, which means that depending on your Reveal settings, like the number of signals or cores or logic analysis that you're trying to implement using Reveal, has an actual impact on the resources utilized in your final device's implementation. Another important thing to keep in mind when using Reveal Controller to interface with your design is that all operations happen with respect to the JTAG clock and should be treated as asynchronous signals as such. Aside from that, another important takeaway that you should remember about Reveal is that there are multiple ways to implement it, whether it be using the hardened JTAG block on your device or using a soft JTAG block, which is implemented using Let's on device. And lastly, one other takeaway that you should know about Reveal is that you can have multiple cores for Analyzer and one controller core, with up to 15 logic analyzer cores currently supported in Reveal. And why this is important is because it's oftentimes recommended to have different analyzer cores for each clock domain, as each logic analyzer core has its own sample clock. However, we'll discuss this a little bit more in the following section, which we discuss Reveal Analyzer. So with that, let's move on to the next section, where we'll discuss Reveal Analyzer in a little bit more depth. So to begin, I want to elaborate a little bit more on the big question here. What is Reveal Analyzer used for? Well, as we touched upon in the previous section, Reveal Analyzer is used to integrate a logic analysis on device and can also be used to implement logical expressions to determine when your device should be capturing signals. Aside from that, Reveal Analyzer can also be used to capture signals at various times during your device's operation, including even on startup using its POR debug functionality. Something that you should always keep in mind when using Reveal Analyzer are some of its design considerations, like the number of signals that can be traced per debug core, which is another limitation and might be another reason why you need to add multiple debug cores for Reveal Analyzer. Each individual analyzer core supports up to 512 total signals, with 15 cores totaling up to 7,680 signals that you can debug at a time in your device. However, one other thing that you should keep in mind, right, is that the number of signals that you're tracing has an actual implementation effect. So if your device is high on resources and does not have many to spare, you probably should not be tracing this many signals and should choose them selectively. And as I mentioned in the previous section, another important consideration is that each analyzer core should have its own sample clock, which is selected during insertion. This is important because each of the signals in your design may belong to different clock domains, and depending on the sample clock, you may not be sampling those signals enough. So aside from that, another thing that you should keep in mind is the speed of those sample clocks, which should definitely be faster than the rate at which the signals that you're tracing should be toggling. Otherwise, you may miss some signals triggering. Another important thing to keep in mind is that these sample clocks also need to be continuous and free running and cannot stop and start midway through Reveal Analyzer signal tracing. Moving on, one important thing to know about Reveal Analyzer are the different types of signals that you can use when implementing this feature. The first type of signals are trace signals and are essentially the signals that you want to show up in your waveform display and analyzed whenever you're debugging on device. These are the signals that you want to tap into within your design. The second group of signals are called trigger signals, which are used to create trigger expressions that determine when Reveal should begin capturing the trace signals in your design. Whenever a trigger expression, which consists of trigger signals, is evaluated to be true, then Reveal will begin capturing the trace signals in your design for whatever amount of time. Another important thing to keep in mind is that you can actually trace trigger signals as well using a setting within Reveal. And another important thing that you should know is that the total signal limit for analyzer cores only includes signals that appear in your waveform display. So these are all trace signals as well as trigger signals if you have the setting enabled, which I'll discuss in the following few slides. So now that we have some understanding of how Reveal Analyzer works, the next big question is, how do you actually use Reveal Analyzer? How do you implement this into your designs? So, like I mentioned, the first step is to identify trace signals, which are the signals that you want to evaluate in your design. So to do that, you would open a Reveal Inserter project, and then add a logic analyzer core, and then drag the trace signals from the menu on the left side into the trace signal grouping tab. At this point, you would need to select a sample clock, which determines how often these trace signals would be captured, which is ideally from a similar clock domain to the signals that you're tracing. Aside from that, there's a few other settings that you could define here, like the buffer depth, which determines how many signals traces you want to capture, the data capture mode, which determines the nature at which Reveal will capture the trace signals, which is either capturing just once or multiple times, as well as other settings like POR debug, which can be used to capture these signals on startup, as well as the setting which we discussed in the previous slide, which is called include trigger signals in trace data, which will include all of your trigger signals in the following tab in your resultant waveform display. Once you've finished adding all the trace signals for your design and have added a valid sample clock, the next step is to add the trigger signals and trigger expressions at which you want Reveal to capture these signals. To do this, you first need to select the Trigger Signal Setup tab from the bottom of Reveal Inserter, and then, once again, add the trigger signals to the trigger unit area at the top, and determine which operator and value you want these trigger units to be equal to, which will determine ultimately how these can be used in trigger expressions. After you've added your trigger units for your design, the next step is to actually add the trigger expressions. Trigger expressions can be logical expressions or can simply be equal to a trigger unit, which you can see from the example on the slide. This first example does an AND operation for the first two trigger units, while the second trigger expression is just a straight up map to the third trigger unit. So as you can see, these different types of trigger expressions can use different types of operators, which we have an example of here at the bottom right of this slide. So some of the different ones that you can use include AND, OR, XOR, NOT, count, and consecutive count. So once you've done this and you finish inserting your Reveal core, the next steps are to perform a DRC using the menu button on the side, and then insert it using the button below that, which is a green arrow-like icon. Once your design contains Reveal inserted, the next step is to regenerate a new bit stream with Reveal inserted, and then program the device using the bit stream that contains Reveal. At this point, now that your device contains Reveal, we can now use Reveal Analyzer and Controller in order to interface with the design. So to do this, select Tools from Radiant or Diamond, and then from the drop-down select Reveal Analyzer, and you should see a pop-up window like the one that appears on the right side of the screen here. At this point, you can open an existing project. However, since we're talking about the new project flow, you would need to create a new project using the first option, where you would define a name for your project, and you would need to select the USB port that your device is currently connected to. After that, you would need to scan for your device and select it there, and then click OK to begin debugging. At this point, Reveal has established a connection with your device. And now that Reveal is connected to your device, the next and final steps are to actually begin debugging. So to do this, you would use the green arrow icon at the top of the window, which would tell Reveal to start probing for trigger expressions. At this point, Reveal would sample the signals in your design, and whenever the expression is evaluated to be true, those signals would be captured for however many buffer depth that you selected in the inserter stage, and displayed in the waveform-like display, which you can see in the bottom right of the figure. These waveform displays display all of the signals that you selected during insertion, and you can also select different radiuses and even define your own custom radiuses as well. So with that said, that's Reveal Analyzer, and that's how you can use it to debug the various signals in your design. So now that we've discussed that, let's move on to the next function of Reveal, which is Reveal Controller, where we'll discuss a few different of its main features, beginning with virtual switches and LEDs. Virtual switches and LEDs. The first question you may have are, what are these? How do you use these? So to quickly give you an introduction, virtual switches, which are exactly as their name sounds, which are single-bit embedded switches that can be directly toggled through software on device to control signals in your device. While virtual LEDs are also like their name sounds, which are single-bit signal taps, which can be used to probe signals in a design and be displayed in a Reveal controller after the fact. One other thing that you should keep in mind with virtual switches and LEDs is that you can use these simultaneously, however not on the same signal, which means that you can control some signals with virtual switches, however you cannot use those same signals with virtual LEDs, as they'll have a driver conflict that way. Before we continue, I want to quickly discuss some user design considerations, beginning with that virtual switches and LEDs can only be connected to wires in user logic, as your design has to be synthesizable with Reveal inserted. Aside from that, another consideration to keep in mind is that you can only have 32 of each, meaning that you can have up to 32 virtual switches and 32 LEDs, totaling 32 of each, so 64 total. And another thing to keep in mind, right, is that these virtual switches and LEDs will have generic names whenever you add them. However, you can also rename them later on in the GUI. And as I mentioned in the introduction part of this training, another important thing to keep in mind with this in all Reveal controller operations is that they happen with respect to the FPGA JTAG clock and should be treated as asynchronous switches if you're using it to drive any of your logic. And aside from that, another thing to keep in mind is that the polling and the reading from virtual LED signals also happens with respect to the JTAG clock. Moving on, the process to actually implement a Reveal controller virtual switch or LED is pretty much the same as what we previously discussed. So what you would first do is create a Reveal inserter project and then add a controller debug core. From then on, you would select the virtual switches and LEDs tab at the bottom, which is actually the default tab whenever you add a controller core and click on it in Reveal. And then from then, you would use the signal pane on the left side and then drag whichever signals that you want to implement in virtual switches or LEDs. So here on the example, you can see that I've added a multi-bit data in and out signal for my virtual switches and LEDs. And then once you've done this, you should do the DRC check again, like we did with Reveal Analyzer core, and then you can insert it and then synthesize your design and implement it on device. Yeah, so like I mentioned, you first need to perform a DRC to make sure everything is good and that your assignments are valid and they're not going to cause errors later on in the flow implementation process. And then insert Reveal to your design. Once Reveal is inserted, you need to generate a new bit stream with Reveal inserted, and then program your device, and then once again create a new Analyzer controller project and connect to it using Reveal. And then from then on, you can begin using virtual switches and LEDs instantaneously. So you can see from the example here on the slide, the virtual LEDs appear at the top and are shown in green whenever the signal is active. We can also select the polling speed at the top, which determines how frequently the sample clock samples these signals. You can increase it to the right to make it a faster polling speed. On the bottom, you can see the virtual switches, which are actual switches in the GUI, which you can rename and then toggle by clicking on them. Aside from toggling directly, you can also directly input the data, which corresponds to a hexadecimal number, which corresponds to each bit of the switches. There's two modes with virtual switches. The first is the mode where you need to apply. So you can see there's a direct mode checkbox. If this is not enabled, then you would need to toggle the switch and then click the apply button in the top right to apply whatever you just set. Otherwise, if it was enabled, you could just directly click the switch and it would be instantaneously applied over the JTAG clock. And just want to reiterate, this is done with respect to the FPGA JTAG clock. So you should treat these signals as asynchronous switches if you're using it to drive your logic. So like I just mentioned, with virtual switches, you can toggle the switches by just directly clicking on them or directly inputting the data into the data field. And then there's the direct mode, which can choose how you want these values to be applied. On the virtual LED side, you can use the polling speed to determine how quickly you want your signals to be sampled, and you can use the stop polling button to start or stop the polling, as well as the polling ones to just poll whatever your signals values are whenever you click that button. So that's it for the virtual switches and LED side. Let's move on to the next topic of discussion, which is user memory access. So as always, the first question is, what is user memory access and how can I use this in my regular design flow? User memory access is essentially a GUI interface which enables direct interaction with the generic memory module in your design, which has generic signals like read, write, read enable, clocks, and so on. You can read or write from these generic memory units and can also load memory files and dump memory address values as well. So these memory modules are implemented using a few generic signals like clock, clock enable, write enable, read enable, the address, the write data, and then read data, which could actually correspond to signals in your design. So whenever you're using user memory access, a couple of the considerations you need to keep in mind is that your design must already contain a memory block, which is interfaced with your regular design. This feature does not insert those memory blocks for you. You have to interface with one that's already there. Aside from that, the inputs to memory module can only be driven by Reveal controller's user memory access function. So you'll need to use some debug signals if you want to interface here, as you'll run into multi-driver issues otherwise. And once again, everything is done with respect to the JTAG clock. So all reading and writing is done with respect to that. Once again, the process for implementing user memory access is very simple. And one key difference to keep in mind is this actually needs to begin before you insert Reveal with some preparation in your own design, where you have this memory module already instantiated, interface with your regular design operation, And if you want to write to the memory module using Reveal Controller, you need to make sure that you're not driving it with any of your own signals, and instead are using wires to connect to it that you can later drive with the Reveal Controller user memory access. So once you've done that, then you can open Reveal, insert it again, create a new project, add a controller debug core, and then instead of the other tab that we mentioned in the previous one, you would select user memory setup at the bottom, and then enable the checkbox at the top. From this point, you just need to assign a few different signals for the generic memory interface using the generic signals which we discussed, which are clock enable, write and read enable, address, and then the write and read data signals. And then once you've done that, perform a DRC again, insert reveal, and then generate a new bit stream with reveal inserted and program your device. And then from then you can begin debugging. And as you can see from the example on the side, the final debugging interface is a pretty simple GUI. It has a few different fields like the default data, which is something you can use to initialize an entire memory with some default data, as well as a read and write address field, right? Which you can choose to determine which addresses you want to read or write from. There's also obviously write data, which will allow you to select what data you want to be written, as well as the read data, which will display whichever data you want to read from the address you select. And then lastly, there's also the option to dump or load memory files. So you can choose which address spaces in your memory you want to dump from. And you can also load it generic memory initialization file to your memory using this feature. So in summary, a few of the things to keep in mind is that you can use this to write to specific addresses, read from specific addresses, initialize entire memories, or generate a memory initialization file by dumping the contents of your existing memory. Or aside from that, you can also use that to verify, the functionality of your design and make sure that things are being written correctly by, exporting the data from your memory. So that concludes this user memory access function. Let's move on to the next Reveal controller function, which are user status and control registers. User status and control registers. The primary usage for user status and control registers actually varies a little bit depending on which you're using. User status registers are used to read from multi-bit signals, while user control registers are used to read and write. So it actually has a little bit more functionality if you're using control signals. Both of these can be used simultaneously. However, you can't have mix and match signals, meaning that you can't have signals that you have as part of a user status register group also be driven by a user control register group. They're mutually exclusive, so you can only use one or the other. In the actual GUI, these are separate tabs, so you can add separate user status and control registers. Similar to the other Reveal controller functions, there are a few similar user design considerations. These are actually pretty much the exact same design considerations you would need to use when using virtual switches or LEDs, which is that you can only connect control registers, which are the equivalent to virtual switches, to wires in your user logic to prevent multiple driver problems. Another thing to keep in mind is that you can add up to 32 8-bit registers of each, which means that you can have 32 times 8-bit status registers, and then another 32 set of control registers. So you can have 64 total, but they are 8 bits each is the limitation. Something to keep in mind is, right, although these support up to 8 bits, it's not required that a signal has to be 8 bits. It could be any variation 1 through 8. And once again, this is all done with respect to the FPGA JTAG clock. So if you're using control registers to drive some signals in your design, you need to keep in mind that those signals should be treated as asynchronous. Moving on, the first thing that you need to consider is actually before you go to reveal once again. So once you're designing, right, you need to have in mind which signals you want to be, monitored using user status registers, or which signals you want to control with user status registers. Something that I sometimes do is I have a separate set of, temp registers, and I'll use an if statement to determine which version of my design I'm generating, right? And if I'm using the version with real inserted, then my design will be driven by these other temp registers. Otherwise, if it's the normal operation, it'll use the regular registers. And the reason that this is important is, like I mentioned in the previous slide, you need to have unconnected wires driving your logic, right? And then in Reveal Inserter, you'll select these wires which Reveal will drive. So you need to make sure that you're not driving the same signal multiple ways in your design. Otherwise, you'll run into implementation problems. So once you've done that initial consideration, once again, you create a new Reveal inserter project, add a controller debug core, and then from the bottom, depending on which you want to add, whether it be controller registers or status registers, you enable the checkbox at the top of each tab, and then you would drag the signals that you want to add as a status or control register into the window. And these can once again be single bit, multi-bit, it can be a combination of signals, and you can also rename these. And then once you've done that, the next step is to perform a DRC and then insert reveal to your design and generate a new bit stream. And then once your reveal bit stream is generated, once again, program the device, connect to it with the Reveal Analyzer controller, and then open up the user status and control register tab, depending on whichever ones you added to your design, and then you can begin using them. So from this example on the screen, you can see what does the user status register look like. It's a pretty simple GUI, so you can see all of the status registers that I've added here, and we can read from each of them individually, or we can read from them all using the bottom button in the bottom left. Aside from that, we can also dump the values that we see using the dump button in the bottom right. So as you can see from the user control register side of things, this GUI looks a little bit different. The main difference here is that there are now a read and write value field. So you can choose to apply different values, right, that you want to write using the write value field. You just input whatever data you want there and then click write. Or you can use the apply all button to apply all the values that you put in that GUI, and it'll sequentially write each value to those registers. Aside from that, you can also read the values, right? So if you write something, you can read it back right afterwards. That's a common usage. And similar to user memory access, you can also load and dump memory files to your registers that you set up here. So that's it for user status and control registers. In my opinion, this is one of the really useful features of Reveal for debugging and interfacing in design, and also determining, whether or not design is working as expected, that it's, functioning in all the different corner cases. This feature is really good for that. So with that said, let's move on to the next and final section of a Reveal controller, which is its hard IP function, which can be used to debug hardened blocks in your designs. So as always, the main question with these features, right, is what are they? How can I use them to help me in my design flow? So, to answer the question at a high level, Reveal's hard IP function is used to tweak the register settings within a hard IP. So depending on the blocks in your design, you might use hardened FPGA resources, right? So depending on the IP, or if you're instantiating these directly, that's one way to implement them, right, to offset the usage of LUTs and that kind of stuff in your design. So these blocks can be tweaked. So Reveal offers the mechanism to tweak these, after the fact, after you've already got it implemented on a board, so that you can see what are the optimal settings. So there's a few different ways that you can use this. It depends also on the IP, and only certain IP are supported. You can do things like PLL modification, oscillator tweaking, PCS channel tweaking. You could generate an eye diagram, or tune a DDR memory interface. So this is also a pretty powerful feature. However, it depends on the hardened IP in your design. So how does this work? This feature provides register level access for the various hard IP in your design, and users can read or write to these registers to tweak the various settings. Another thing to note is that Reveal provides some commonly modified settings as well, so you can just directly modify some common settings depending on the IP using a drop-down or something like that, or like a checkbox, right? Moving on, one thing that I want to touch on, right, is like I mentioned, the various devices that we support have different hard IP, and all of those hard IP, there's actually a subset which are supported in Reveal. So the time of recording for Nexus family devices, which are families like Crosslink NX, Certus NX, Certus Pro NX, etc. Some of the IP we support are PLL, DPHY, I2C FIFO, SGMMI, PCIe, PCS, and so on. On the Avant side, there's PLL and MPV5, however, we have plans to add more. And aside from that, some user design considerations. This is more something to keep in mind with the design's operation with how Reveal functions. So whenever you enable an IP for tuning with Reveal, Reveal will insert a MUX to the LMI bridge, which is used to write and read from the registers in that hard IP. Um, During Reveal usage, Reveal will take control of this MUX to interact and interface directly with the hard IP. However, aside from that, whenever Reveal is not using this to tweak the register settings, which should be a small, subset of whenever you're using this feature, um, it will relinquish control to the regular user design operation. So how do you use this feature? It's pretty straightforward actually. So like all the other modes, it's as simple as inserting Reveal Inserter and then selecting the Hard IP Setup tab once you've inserted a controller core. From there, if you see any supported hard IP, you can enable them using the checkbox, as you can see from the screenshot at the top. And then once you've done that, perform a DRC, insert Reveal, and then generate a new bitstream and program your device. And then once you've opened the Reveal Analyzer controller project, you can see the GUI, which would appear at the bottom, which is similar to the user memory one, right? Where you can write and read from certain addresses, load a memory initialization file, or dump one, etc. So that's Reveal hard IP functionality, and that concludes this part of the training. So before we conclude this training, let's quickly get into a summary of what we've discussed so we can talk about the key takeaways. So if there's anything you take away from these training, I want it to be these three main points. The first is that Reveal is a pretty powerful and versatile debugging tool, which has a lot of different features that are supported, which can do things to capture signals on device, directly interface and control signals in your design, or do other things like fine-tune the hard IP blocks in your design. Aside from that, Reveal is very versatile in that it can be used during various development stages, whether it be the initial RTL implementation, or later on during the implementation flow after synthesis or even place and route. Aside from that, the most important takeaway that you should know is that Reveal is your friend. It's something that you can use to diagnose issues and also use it to verify, your design's functionality at various corner spaces. So that ultimately concludes this part of the training. Before we finish everything off, I wanted to quickly go over a few commonly asked questions that you may have, and if you have any other questions, you can put them in the chat. So to go over a couple of commonly asked questions, the first is how much of Reveal is scriptable? The answer is pretty much all of it. Everything that you see in the Reveal GUI has a corresponding tickle command, which you can use to automate, the Reveal process. So pretty much everything in Reveal is scriptable. Can I use Reveal with other types of debugging? Actually, you can. So if you're familiar with Lattice Toolflow, we also have other types of JTAG debugging like OpenOCD and Propel. So we do support simultaneous debugging with those two features. How is Reveal implemented on device? This is a very common question. So it uses actual FPGA resources. So depending on how you set Reveal, it may use different amounts of resources, so on. But it's implemented using actual resources on device. Can Reveal be used for protocol debugging? So not explicitly, you can use the Reveal Analyzer to set up different conditions that might happen during a protocol's transaction, that kind of thing. But there is not currently any kind of protocol debugging support directly. What devices support Reveal? This is a pretty straightforward question, although we get it sometimes. All devices support Reveal. One thing to keep in mind is that various Reveal controller functions like hard IP, it will have different hard IP which are supported for different devices. So as you may recall, there's a different set of IP which are supported for hard IP tuning with Nexus devices versus Avant devices. So that's the only thing to keep in mind. Aside from that, any device can pretty much use Reveal. You can use Reveal Analyzer with any device in Radiant or Diamond. And that's actually one other limitation to think about is Diamond doesn't support Reveal Controller. So if you wanted to use Reveal Controller, then you can only use it in Radiant. When should I use Reveal? So Reveal is a very versatile tool. You can use it when you run into problems, but you can also use it in any stage, right, to make sure that your design is operating as expected. And a last question, how can I learn more about Reveal? So we have a lot of different documentation that's bundled with our tools, tutorials. So if you go to our Radiant or Diamond web pages, you can access any of those and check those out to learn more about Reveal. So anyways, that concludes the frequently asked questions part of the training. Before I finish everything off, I just want to give everybody a quick thank you for your time and attention during this training. I hope that you guys were able to learn something that you can take away and use later on. So yeah, thank you everybody and have a good one.